All right, so in this video we're going to talk about different types of spectroscopy. So we have actually talked about it a little bit. We talked about a PES diagram, and then PES diagrams are good for determining the energy level of the electrons and then the positioning of the electrons in an atom. Now, spectroscopy, as in general, is the study of interaction of electromagnetic radiation and matter. So electromagnetic radiation, remember that's anything on the EM spectrum, so infrared, X-rays, gamma rays, microwaves, all of those things are radiation. So if you were to take a sample of matter and bombard it with some sort of radiation, that radiation can be measured before and after. So how much, so if we have a sample of some sample of matter, and then we take some type of radiation, okay, and then we bombard that sample, we can measure the energy coming off of it, okay, and then we can know how much energy was absorbed in the sample. Now, different types of infrared or different types of radiation will interact differently with the sample, and they can tell us different things about that sample of matter. So, one of the most common types of spectrums is an IR spectrum. So this is an IR spectrum, this would be a UV spectrum. And essentially in an IR spectrum, you take your sample of matter, it's usually some sort of compound, that you're going to try to determine what that compound is. Now, an IR spectrum can tell us what types of bonds you have in that compound. So if I'm looking at this one right here, I know that it has a carbon double bonding to an oxygen because of this peak right here, because of the way the peak looks and also where the peak is on this graph. And then I can also tell it's a carboxylic acid, which means it has a carbon double bonding to an oxygen, which is also attached to an alcohol group. So infrared radiation, if you take a sample of matter and bombard it with infrared, that energy gets absorbed into the bonds and will stretch and vibrate the bonds in certain ways depending on what type of bond you have. And then at the end, how much energy is either absorbed in that substance or transmitted through will be absorbed, and then we produce a spectrum that looks like this. So an IR spectrum can be used to determine the types of bonds, and one of the most important things that you need for this particular course is you need to know that infrared radiation will vibrate the bonds. That is how that radiation interacts with matter. It vibrates the bonds and compounds. Now, this is a UV spectrum. So essentially what you do, you take your sample of matter, you're going to bombard it with UV radiation. The UV radiation will be used to excite electrons, will cause the electrons to jump up in energy and then also fall back down, and then you're going to measure that energy change as that happens. So what you need to know with that is that UV radiation will cause electron transitions, or it excites electrons. All right, this is just one of those things. I've seen it come up on almost every AP exam that I've seen. There's usually like one question about how radiation, different types of radiation, interacts with matter. So UV and visible light, okay, will be used to cause electronic transitions. Okay? Infrared radiation is going to be used to cause molecular vibrations. And then microwave radiation will be used to cause molecular rotations. So it's going to rotate different aspects in the compound. So that's really what you need to keep in mind with this. I also have another sheet with information on the different types of radiation and how it interacts with matter. I would definitely suggest you look at that sheet. These usually aren't hard questions, so they're easy to get, but they're also easy to miss if you don't just remember it. All right, so on the EM spectrum, you have different types of radiation. You have gamma rays, X-rays, ultraviolet, UV, visible, infrared, microwaves, and radio waves. So starting with radio waves, we have the lowest amount of energy. It's the longest wave with the lowest frequency. As we go out to the gamma rays, we get more and more energy. And remember, gamma rays are the most harmful, and they will have short waves, so short wavelengths, and a high frequency. All right, so one of the ways that we use visible light is with a spectrophotometer. So a spectrophotometer is a device that we use, and it takes visible light, you bombard a sample with it, and then you're going to measure the visible light after it passes through a sample. So usually it's going to be in a cuvette like this, and you aim light, so visible light, through that sample, and then you measure the visible light at the end to see how much visible light is absorbed in the sample. Now, a spectrophotometer using visible light, you can only have a colored solution. So if you have a solution, like a salt solution, NaCl in a solution, that isn't a colored solution. You cannot do anything with visible light and a non-colored solution. So it has to be something that's colored. Now, if you look at the periodic table, most of the elements that are going to produce colored solutions are going to be transition metals. So now zinc will not be a colored solution, but most of the transition metals do produce colored solutions, and we can use a spectrophotometer to measure the absorbance in that solution. Now, why do we care about that? Well, the darker a solution is, or the more solute you have in the solution, you're going to have a different color, and you're going to have a different amount of light being absorbed. So the more concentrated a solution is, the more light that is absorbed, and the less light you're going to measure as it passes through the sample. So the amount of light that you measure at the end can tell you how concentrated a solution is. So usually we'll do this with something called a calibration curve, which I'll show you in a few minutes. So we can measure either the absorbance, so how much light is absorbed into the solution, or the transmittance, which is how much light passes through the solution at the end. So primarily, we're going to use this for determining concentrations of colored solutions. Now, when we use a spectrophotometer, we have to pick a certain color. Now, the color that we're going to pick is going to be the complementary color. Okay, so whenever you see, when you have a color that's observed, that light is actually being reflected. So if I have a blue solution, blue light is being reflected. So remember, we're looking to see how much light is absorbed. So we have to pick the complementary color because that's the color that's actually absorbed. So if I have a blue solution, I would pick an orange wavelength setting. So I would pick somewhere between 600 to 604 nanometers. If I were to have a yellow solution, so the color is yellow, okay, it reflects yellow light, I would want to pick the complementary color, which is going to be violet. So I would want to set that wavelength to 400 to 450 nanometers. So on a spectrophotometer, you have a knob, or you have a way to set the wavelength that you're going to aim at that solution. So you're going to pick the complementary color because that's the color that's going to be absorbed. Okay, so something else to note is the Beer-Lambert law. Now, the Beer-Lambert law is a mathematical equation that relates concentration and absorbance. So the Beer-Lambert law is actually big A is equal to little a times B times C. So big A is the absorbance. There are no units for that. Little a is going to be the molar absorbativity, which is a constant. That's going to change depending on what solution you have, etc. B is going to be the path length. That's the length of the cuvette. So how much space does that light go through? So how big is the cuvette essentially? And then C is going to be your concentration. All right, so let's find the concentration of a solution with the absorbance of 0.16 with a molar absorbativity of 960 liters / moles / centimeters. So for this, you just simply plug everything in to the equation. Okay, so that's way off. All right, so A is the absorbance. Remember, there's no unit for that. Little a is going to be our constant, which is 960. B is going to be the length of the cuvette. Now, centimeters and centimeters, that matches, so that's good. It's usually in centimeters anyway. And C. So now at this point, you're just going to solve for C, which is going to give me 0.00016 moles per liter, because it is concentration. Or we can say 1.6 times 10 to the negative fourth. Okay, more than likely you're not going to be asked to use this equation to solve for it, but they could easily include it. So I just wanted to go over that. So this equation is used to find the concentration given the absorbance. So once you take a sample of matter or a solution, you put it into the spectrophotometer, you measure the absorbance, and you want to know what the concentration is, you can use this equation to get that. All right, so this is a calibration curve. Now, this is done a lot in chemistry labs. So a calibration curve, okay, is going to be a graph. It's going to be a linear graph that you can use that graph to determine an unknown amount. So it depends on what you're graphing. So a calibration curve can actually be used in a lot of different ways. You could have density and concentration. You could have different amounts for the y-axis. So absorbance versus concentration here. So how much light is going to be absorbed depends on your concentration. So what you essentially do is you take solutions where you know the concentration, okay? You know what that concentration is, and then you go to the spectrophotometer, you insert it, and then you measure the absorbance. How much light is absorbed at that point? Then what you'll do is you'll plot it. You're going to get a line, okay? And essentially what you're really after is this. The y equals mx plus v. So they did actually teach you this, and this does have a very practical application here. So y will be whatever your y value is. So in this case, and in this particular graph, it's the absorbance. M is going to be your slope, okay? X will be your concentration, because that's what's on the graph. This is the x-axis and the y-axis. And then B is going to be your intercept. Once you have this equation right here, okay, what you can do with this is you can take a solution where you do not know the concentration, so you don't know the value of X, and then you can take it to the spectrophotometer, put it into the machine, measure the absorbance, so now you know what the Y value is, so you know what the absorbance is, and once you have this equation, well, you know what the slope is, and you also know what the intercept is. So then you use this equation to solve for the concentration. And we use this a lot in chemistry. So in chemistry, remember, we answer two questions primarily. What is it, and how much do we have? Well, a calibration curve can be used to determine how much we have. Now, something that I could see them doing on the AP test, and I have actually seen them do this, is where you have that calibration curve, and they ask you, okay, you have a sample, you measure the absorbance, it happens to be 0.2. What's the concentration? So then at that point, you just go and you'd read the graph, and you'd say, okay, 0.2 right here, because it's on the line, and then I just go down and measure what the concentration is.